So there was this Collatz Conjecture. Seemed like an interesting thing. And I saw some videos about it. I was trying to figure out, like, okay, what is it that people are having a problem with it? Because it was just the idea that it's like, the video that I saw was, it said uncrackable. So it's like, okay, uncrackable conjecture apparently. And then it's like, all right, well, what is it about? What makes it uncrackable? And then, it showed the equation, like how you do it, which is, yeah, let's bring out a calculator real quick. So we can do a little bit of the math. So the idea is 3n plus 1. So the idea is n is a number, right? So you pick a number and then you do the equation. So if the number is even, an even number, then you divide it by 2. If it's so that means you do the first part of the function. You divide by 2. But if it's an odd number, then you do 3n plus 1. N will be the odd number times 3 plus 1 after you do the 3 times whatever the number is. So it's like, all right, a simple process. So let's say I choose the number, I tend to go with 4. So 4, obviously, is an even number, so divide it by 2 will give you a 2. 2 is also an even number, so divide that by 2 gives you a 1. 1 is an odd number. And that was the other thing, is when you do this function, it's the idea that no matter what number you put into, you choose as n, no matter what number you choose to do this function, it will always get down to 1. They always one of the things they said is like, they don't know if it will always go down to 1. So that was the thing. So we'll get to that soon, but let's do the function again. So since I have 1, which is an odd number, we will times it by 3, which will give you 3 plus 1 will give you 4. And then 4 obviously is an even, so divided by 2 gives you 2, divided by 2 gives you back down to 1. So you see, you keep going back down to 1. So once you get to 1, you keep doing the function, you just keep going back down to 1, obviously. So then, let me take that away. So then the questions was does the function go infinite? So no matter what number you choose, will it always go down to 1? So will the function always function, as it were? Will it always equal 1? So no matter what number you put, will it always equal 1? Now the idea is a positive number. So no decimals, no 2.5, 1,000,000.5 or 1,000,000.111111 or something like that. So it has to be a whole number, you know what I mean? Like 1, 2, 3, 4, whole number. 1,000, 1 billion, you get the idea. So they're curious about, will it go infinite? Can you infinitely do this? The answer to that is yes. As you can see on my second part, I put out my answers right here to these 3 questions. Does the function go infinite? And if yes, why does it go infinite? You gotta be able to explain why it go infinite, right? You can't just say, oh yeah, it goes infinite, because then you're just assuming. Why does it go infinite? So you have to be able to explain why it goes infinite. So answer 1 is yes, it goes infinite. 2 is why it goes infinite. And the reason it goes infinite is that the 3n plus 1 function creates an infinite loop between going from even number to odd number and vice versa. I noticed that every time think about it, whenever you have an even number, you have to divide it by 2, right? Notice 2 is also an even number. So any even number divided by 2, which is another even number, will equal out will give you a even number until it gives you an odd number. Because 6 is even, but when you divide 6 by 2, it becomes 3, which is odd, right? Notice you're constantly you're transitioning from even number to odd number. Once you get to odd, then that's when you do the 3n plus 1 part, which is 3, which is an odd number, times 3, which is another odd number, gives you 9, which is also an odd number. But then when you add 1, it becomes a 10, and 10 is an even number. So notice that anytime you get like 3, add the 1, it becomes a 4, which is even, right? 5 is an odd number, but add 1 to it, it becomes a 6, which is an even number, and keep on going, right? You have 7 is odd, but you give it a 1, it becomes 8. And then when the way you add up, like when you count, right, you go 1, 2, 3, 4, 5. When you count up, especially to infinity, right, you're always adding 1 to those numbers. So if you have a 10 and add 1 to it, it becomes an 11. If you add a 1 to an 11, it becomes a 12, and you keep going, and that's the whole process. So you notice this thing goes back and forth between an odd number and an even number, and then it adds 1. But you notice the way we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? We're always adding 1. So this conjecture will always, no matter what number you give it, as long as it's, you know, a whole number, not a decimal number, you know, 1.5, 1, 12, you know, 12.7 or some shit like that, it will always give you a, you know, even or odd number, and then you do the function until you end up all the way down to 1. The way I look at it is that you got to look at whatever number you think of, right? If you think of 1,000, that's you taking 1,000. You start at 1, right? You start at 1 is your starting point. You start at 1. You move 10 space forward. 1,000 space forward, right? Do you know? And then you start doing the function, which will always cause you to go back. Since 1,000 is an even number, right? You'll divide that by 2, which means you're taking half. You know, you're going back half the. Okay, you're dividing 1,000 by 2, which will equal 500. So you take 500 steps back. So if you take 500 steps back from 1,000, you end up at 500. Then 500, you can also divide that by 2. So you get 250. So you divide that again, right? So you're taking 250 steps back. So you're at you're at 250. Then 250 can be divided again. So 125. You know, you take 125 steps back. But once you get to 125, that's an odd number, because you'll get into decimals if you divide by 2. So then now you do the multiplication, and you get to 250 plus 1. So you have 251. And then you keep doing that process over until you eventually get down to 1, because the whole idea is you're always taking more steps back when you're dividing by 2 than you are taking forward, which is plusing 1. So mathematically, you will always go back to 1 eventually, because you're constantly halving every time you get an even number. And when you plus an odd number, you know, you give plus 1 to an odd number, you instantly turn it into an even number. So you take a 3, turn it into a 4 when you give it a 1. You take a 5, you give it a 1, you turn it to a 6, right? You go from odd to even, odd to even, odd to even, and then you're rolling back times 2. Rolling back by 2, you know, by half. You're greatly taking steps back whenever you divide by 2 before you multiply and go 1. Now the multiplication is times, anything times 3 would be a big number. So if you have a 10 times 3, for example, 10 is an even number, but I say 7 times 3, right? 7 times 3, these are two odd numbers, will equal to 21 plus 1 equals 22. 22 is an even number, so cut that in half, it's 11, you know, and 11 is an odd number, so you do the math, and you're going to go up, but then you're going to greatly go back down once you divide by 2. Once you get to the point where you divide by 2, the number is going to go down, so it's an up and down, it's up and down, an up and down pattern, like a wave function. So there's that, which is why you always reach 1. But the thing is that no one ever points out is why you never reach 0, right? Why you never reach 0 or reach 0.5, because half of 1 is 0.5, right? It's half of 1. But why you never reach that? Why is always 1? The reason why is because once you get to 1 is an odd number. The function will always cause you to multiply by 3, which will give you 3, which is still an odd number, plus 1, which will be 4. Now it's an even number. You divide by 2, you get back down to 1. It's like, yeah, you're always going up, back down, going up, back down. So it's an up and down pattern. And the fact that once you get to 1, you never go down, because you're never dividing by 2. You never divide by 2 once you get to 1. So of course, the function, no matter what number you choose, it will always go back down to 1, and that's why. So yes, this will happen infinite. Even if the number you choose is 1 trillion, you start doing the functions, you're going to go back down to 1 eventually. It'll take a lot of steps to do so. It's going to take a long time because you're constantly going up and down, up and down, up and down. But you will eventually get there. So the third thing is also what number doesn't equal 1, if any. And that's another thing that people wanted to know is what number can you put as n that won't equal 1, that will give you like maybe a 2 or something, or a 0, you know. And interesting enough, obviously if you choose the number 0, it will always be infinitely 0, because you're always, since 0 is an even number and you're always dividing 0 by 2, you're infinitely dividing an infinitesimal number, which is 0, and you're infinitely doing 0. So your answer will always be 0, infinitely. So that's another way of obviously knowing that this conjecture would give you an infinite of something, infinite 0 or infinite 1, no matter what number you choose, because of how the steps are working. So that's why I put n equals 0. 0 is an even number, and it will infinitesimally divided by 2. So that's a number you can punch in that will infinitely give you a 0. So you never will get a 1 from picking 0. If you pick 1, obviously you're gonna do the function, which is just gonna bring you up immediately to 4, and then you go from 4 down back to 1 and infinitely loop there. So that's another thing. So obviously you would this will go in, you know, it will go infinite. I mean, it's hard to believe that it wouldn't, you know. So it's weird that it seems like some people want to think like, what would this actually go infinite? Like, what is the number that could break this conjecture? It's like it won't, because the way this conjecture functions, it will always give you that same result. It's designed specifically to give you this infinite up and down function. This whole, you know, go up, multiply, times 3, plus 1, right? And then eventually when you get to an even number, go down by 2, right? Divide in half, cut that in half, and just go up, cut down in half, go up, cut down in half, go up, cut down in half. So a side note is the idea that I believe infinity is a superposition, where if you look at it, when you're trying to count from 1 to infinite, right, or to a billion or a trillion or something like that, it's always 1, 2, 3, 4, 5. You get the idea. It's always an odd number, then an even number, odd number, even number, odd number, even number. So the idea of it being a superposition, that infinity is half even numbers and half odd numbers, which is why I'm calling it infinity superposition, because it's 50% of it is even numbers and 50% of it is odd numbers. No matter how big the numbers are, there's approximately same amount of equal amount of odds and even numbers, 50-50, right? So there's that. Another side note is gravity might be a superposition force, or a byproduct of subatomic particles switching from positive to negative, like positive to negative charge. So that's an interesting thing. I'll start thinking like, what if that's how gravity functions? Because the way this conjecture works, you know, like I said, the way I was explaining it, how you take, you know, 10 steps forward, and then you end up taking 5 steps back, and then you end up taking, you know, then take the 5 and move times it by 3. That means you're taking 15 steps forward. Then you're adding 1, so you become 16. Then you take that, cut that in half, and go back by 8 steps, right? And 8 is less than 10, so obviously you'll be at 8, you cut it in half again, so you'll be at 4. Then when you're at 4, you'll go down to 2, and anytime you get to 4, obviously you're going down 2, 1, and then back up to 4, and then 2, 1, 4, 2, 1, 4, 2, 1 is a constant repetitive loop. So you always go that back down to 1. So you see that idea. So I was thinking like, what if gravity works that same way, where, you know, you throw something in the air, it's taking, let's say it's taking, you know, 10 steps, 10 feet. Like you throw something 10 feet in the air, it's like, all right, now it's 10 feet in the air, but then eventually the conjecture kicks in and it starts coming back down, you know, starts coming back down because of the function of, you know, positive and negative particles or ions or whatever you want to call it, and then that's how it functions. Just an idea of like, that'd be interesting if that's how gravity works. Is that gravity is basically a superposition. It's both positive and negative, but it's constantly switching between positive and negative, and it kind of does a little bit random. I also notice a thing about this conjecture is that when you punch in like different numbers, you notice that the processes it takes to get back down to 1. You notice there's like some odd patterns with the numbers. It's not always perfect straight up, straight down, making a like a triangle type, not triangle, but like upside down V type pattern. I'm not gonna waste time trying to do some drawing. Oh, why not, right? Which might as well, since I'm already doing the video, I might as well add more visuals to it. So the idea of like the conjecture normally goes up, down, down, right? But sometimes it can go up, down a little bit, up again, then greatly go down, then go up a little bit, up, down, down, up, down, up, right? Go up and then down, up. You get the idea, right? That's not perfect, but you get the idea that sometimes, depending on the number, it will vary on how it's like, how many steps it's taking, and how the wave, if you're actually graphing it, in a wave function, how it will look. And it'll look something like this. Like some numbers will create a pattern like this of of you going up to a big number and then going down to a slightly smaller number, and then greatly go back up to a bigger number, because you're doing the 3n+1 function. But then when it turns out to be an even number, you cut that in half, right? Divided by 2, you greatly drop back down to a much lower number, half that, and then you start going back up and down, especially if you're doing a lot of odd functions. I mean, a lot of even functions, you'll go down. Once you go odd again, boom, you times 3, going right back up, and then +1, and then when it becomes an even number, you drastically cut it back down by 2, and then you get the idea. And that's how I've been seeing this conjecture play out. Now I'll show you some other stuff here. So obviously I rearranged the conjecture a little bit. So you see, this is the regular one, this one right here. This is the 3n+1 conjecture. So I was like, all right, well, what if you change the 3 to a 2? What will cause it to always hit 1? In this scenario, what happens is it's even numbers. So you take you take a number. What? That's right. Take a number times 2. So if 1 times 2 is 2, if 2 times 2 is 4, then 3 times 2 is 6. Okay, yeah, that's what it was. So whatever number you put in, times it by 2, will give you a number. So if you put in 3, which is an odd number, times it by 2, it becomes an even number, because it becomes 6. Then you divide it by 2, which becomes 3, and then you get the idea that you take. And then when you do this function right here, which is you take that 3 plus 2, times 2, will give you 6, plus 1 will give you 7. 7 is the odd number, so you do the function again. 7 times 2 is 14, which is an even number, but to give it 1, it becomes 15. And then 15 is an odd number, so you times it by 2, which will give you 30, which is an even number, but then give it 1, so then it becomes 31, which makes it back into an odd number. So then, that kind of will play out over and over again. But eventually you will get back down to 1. So if you use the calculator, interesting enough, there's an app that I was using when I was testing out these ideas that way better than what I do, because even I can make a mistake and assume a certain number is odd instead of even. So let's go back. What was I saying? The 7, was it? No, 2 times 3, right? Yeah, 2 times 3. So let's go with 2 times 3 will give you 6, plus the 1 will give you 7. 7 is an odd number, so then you have to do the function again, which is 7 times 2 will give you 14, plus 1 will give you 15. Oops, did that wrong. Go 14 plus 1 obviously will give you 15. All right, so 15. Now let's divide 15 by 2 and see what happens. It's 7.5, so obviously that doesn't work. So back to 15. So 15 times 2 equals 30, plus 1 equals 31. Divide that by 2, let's see what happens. Again, doesn't work, right? So it's still an odd number. So 31 times 3 equals 93, plus 1 equals 94. Divide that by 2, see if that works. See, now we finally got to a even number. So 94 is now gives you 47. Let's see if we can divide that by 2. No, so we gotta go back to 47. All right, so 47. So this is an odd number, so then we times that by 2, which gives you 94, plus 1 gives you 95, and you get the idea. You're gonna have to keep going, and I don't want to waste too much time going through the whole process to try to get this thing to cut back down. All right, so I notice a pattern that some of these functions okay, so certain these n times 2 functions versions that I'm showing is they will always give you one of two results, which is either you're infinitely going up, just constantly going up the numbers, or you're constantly going down to 1. So these functions, these n times 2 functions that I have, they will give you one or the other. The main thing is that if the numbers tend to be odd, if the numbers are odd, they tend to give you infinite. You just keep going up, 1,000, 2,000, trillion. You go up instead of going down to 1. But if you have it where it's an even number, it's more likely to go down to 1. So these show that as long as the numbers are constantly even, you're constantly dividing by 2, so you're constantly bringing it down to 1. Because once you get to 2, and 2 divided by 2 equals 1. So that's the idea. So this shows that as long as the function is set up in a way that you will always get an even number, so you're always cutting it back down to 1, it works. So as you can see, 0n plus 1 gives you 1s. 1n plus 1 gives you 1s. But the 2n plus 1s don't automatically give you, not every number will give you 1. It's mainly the positive numbers. The even numbers tend to give you 1. The odd numbers tend to not really work so well. And then 3n plus 1 equals 1. So as you can see, and we keep going, this one, now you got the question mark ones. Those are interesting, right? The question mark ones, because you see there are ones that I have question marks on. These are the ones that like they don't seem to line up properly, because some numbers do equal, get down to 1, but then some just don't. And then I noticed there was like a pattern. I kept putting 1 if it did go down to 1, put 0 if it just basically went to infinity. Like the number just kept going higher and higher and higher and never went back down. And then I noticed that it looked like what is it called, a binary number. So it would be something like this. So like, let me see. So it will look something like this, where like if I choose the number, so if I choose 1 and then do a function for this question mark 1, right, then let's say I get the 1, right, I get down to 1, but then the next one I do the function of the number 2, but then it gives me 0, and then the next one will be 3, it gives me 0, and then I do 4, it gives me a 1. It's like it goes down to 1. It's like, okay, so the function will give me, if I put 1, it'll get me down to 1, obviously, right? But if I put a 2, it will go into infinite. If I put 3, it'll go into infinite numbers. If I put 4, then it'll drop down to 1. But then if I put 5, it'll go down. It'll go infinite. 6 will go infinite. 7 will go infinite. But then when I reach 8, it goes down to 1. So then it's like, okay, certain numbers will have a pattern to go on. So then I just skip real quick and just go like, so the next one will be 16 will give me a 1, then 32 will give me a 1. So then it's like there's a pattern there. And then you're timing these numbers by 2, so 32 times 2 is 64. So the next number 64 will through the function will go down to 1. Whatever 64 times 2 is, that'll be 128, I think. Yeah, 128. So the next number will be 128. So there's that. But in between these numbers of this 4 right here, right? 4 times 2 is 8. 8 times 2 is 16. 16 times 2, you get it. Between them, you see like the 5, 6, and 7. There's certain things that happen. Just like between the 0 and 4, or 1 and 4. You notice that this one gave me went down to 1, but all the other ones didn't go down 1. The other ones just kept going up in numbers, just like 5, 6, 7, and this 4 and this little slot kept doing that. And the same goes for 16, 32, and so forth and so forth. That the numbers in between, it's going to be pretty random. There's like a level of randomness in there, but it's always either it goes down to 1 or it goes to infinity. But then I notice patterns that that within those 4 spots, you would get certain things. Like you'll get 4 numbers together, they're next to each other, like let's say, I think it was the number 11, 12, 13, 14. 11, 12, 13, 14, those numbers will always give you just big numbers. Like they'll just keep multiplying up, up, up. They would never hit an even number. They will always just go odd, so the math will always go up. That's the thing, is when the number always turns out odd through the function, you're always using the odd function part, which is 7 times n plus 1, and you keep getting an odd number. You're just going to keep infinitely doing that. So obviously you're just going to keep going higher, higher, higher up the numbers in that process. But then you get one line of numbers, they're right next to each other, for example, they just will give you 1, 1, 1, 1. So let's say it's 20, 21, 22, and 23. You put in those numbers into this function, they will keep hitting down to 1. Now this is hypothetical. That line, those numbers, I don't think, I think 20 does go down to 1, but 21, 22, and 23 don't go down to 1. They'll just go 0. But you get the idea that I noticed that some of these have that. So the question mark ones are the ones that have these like random binary code looking type stuff. I was even trying to see, like, is there a message here? Somewhat it does give you letters. It does give you binary letters when you punch in some of these like 8 to 10 digits, but obviously it's just for fun. But it'll be interesting that these types of equations will give you like some binary messagings or something. Like you'll literally find some binary code within these functions popping up. If you're going with the whole like 1 means it always the function always gives you a 1, but then there's times where it don't give you a 1. You'll use 0 as a representation of this number will go infinite. Like this function will infinitely happen. So you either do an infinite loop up the number scale, or you infinitely go down to 1. So it's one or the other, one way or the other way. It depends on the direction you're going. So you infinitely go up or going to infinity, or you're infinitely going down to infinitesimal, but then you never reach it because you never go from 1 to 0. You always go just down to 1, because as soon as you get to 1, you always do the function and go back up. So you never go down less than 1, because you're always going back up once you get to 1. And you go down all the way down here to 10. You notice that right here you see the question marks, and then you see the N2 versions. You notice that it hasn't changed back to the to the 1. So you notice 0, 1, and 3, you know, will give you 1s. No matter what number you put in that is not 0. So as long as you put a number that's 1 or higher, it will always give you 1. It will always go back down to 1. But any other version of this equation will give you different results, and some of them work with the, you know, work n2. You notice 8 and then 6, and then you notice 10. Since those are obviously even numbers, they tend to be n2, you know, n times 2 functions that will always give you 1. But then there's the odd number ones like the 9 and the 7 and the 5. They're the ones who give you the question mark ones, because they're the ones who will give you a lot of even numbers. So you're always going up the scale of counting, of, you know, doing the function. You never go back, you know, you never go back down to even numbers. You never get an even number, so you never go back down to an even number per se, except for sometimes you do. So that was the idea. Whenever you get you get down to 1, oh, there's a number that got down to 1 from this function, therefore it does go that direction. But it doesn't always go down to 1. A lot of times it goes, you know, the numbers go up, it goes to 0. So it's like, seems a little odd there, right? So these are some stuff to think about, have a little bit more fun. I believe this is a proof that shows that you know, the 3n, the Collatz conjecture does go infinitely to 1 is what I'm saying. It always does go infinitely to 1 because of the way it's set up, the way the function functions. It will always go down to 1. It's designed that way. And I already explained the function of y, the process of y does that. It goes up it goes up and then goes down, goes up and goes down, and it's designed to just keep doing that over and over again. I am experimenting with other versions of the equation. You know, instead of n divided by 2, why not try 3 or 4 or 5 or 6, you know, and see what happens there if you're constantly changing this number right here. You know, if you're always dividing by a different number, what will happen? Especially if you keep it at 3n+1, but this will be a 4 or 5 or 6 or 7 or 12 or 1,000, you know what I mean? What will happen? Obviously that would take a long time to lay all that out, but you want to experiment with a little bit. So this should be the proof for the Collatz conjecture, explaining why it functions the way it functions, and that it does function infinitely. You know, it's like you don't have to worry about like what is the limit, what's the highest number the n can be that will never that would not reach 1. It's like, well, currently it will always reach 1. It's just how long it takes to reach 1, that's a different story. But we don't care about how long it takes to get to 1. What matters is, does the function always will, no matter what number you use, always get down to 1? Can you always break down any number that you can think of down to 1 through this conjecture? Which the answer is yes. And that's the end of the video.